Today's China has become a world-renowned infrastructure powerhouse. One after another major bridge, the construction of high-rise buildings, all are closely related to concrete. In this lesson, let us learn together mechanical properties of concrete for bridges and test detection methods. This section covers the following key points. Mechanical properties of concrete. Concrete specimen preparation method. Test method for compressive strength of concrete. Below we will study each point individually. Raw materials for concrete include cement, water, sand, gravel, admixture, mineral admixture, etc. Ordinary concrete is typically made of cement, water, sand, gravel and other materials are mixed in proportions as required by design. When needed, appropriate amounts of admixture and admixtures shall be added. Among the constituent materials of concrete, sand, stone is aggregate, acts as a skeleton for concrete. Among them, small-sized aggregates fill the voids of large-sized aggregates. Cement and water form cement paste, coating all coarse and fine aggregates' surface and filling the voids between aggregates. Before concrete hardening, cement paste acts as a lubricant, imparts fluidity to concrete mixtures. To facilitate construction, acts as a binder after concrete hardening. Bind sand and stone aggregates into a hole to develop strength in concrete, becoming a hard artificial stone. Various raw materials used in concrete engineering. All shall comply with current national or industry standards, and their performance and quality should be inspected upon arrival. Concrete performance tests include compressive strength, axial compressive strength, static compressive modulus of elasticity, splitting tensile strength, flexural strength, etc. Size of specimens should be based on the aggregates in concrete. Select the maximum particle size according to the table. This is because in concrete specimens, existing defects such as pores and micro cracks will affect the actual stress-bearing area of the concrete specimen, reduce and stress concentration, leading to reduced concrete strength. The smaller the concrete specimen size, the higher the measured compressive strength value. Concrete performance test equipment includes mixers, test mold, pressure testing machine, etc. All equipment indicators shall meet relevant specification requirements. Production requirements. First, conduct an inspection of the test mold size. Focus on surface flatness and angles. Apply release agent. Second, mixture sampling. From the same batch of concrete, or sample from the same batch of concrete. The sampling quantity is 20% more than the required amount. Conduct slump or Vive test within 5 minutes. Begin making specimens within 15 minutes. When mixing in the laboratory, measurement accuracy should meet cement, admixture, water, admixture plus or minus 0.5%, aggregate plus or minus 1%. In the end, molding time should not exceed 15 minutes. The forming method requirements are as follows. When slump is less than 25 millimeters, insert and vibrate for forming. Slump greater than 25 millimeters, and when less than 70 millimeters, a standard vibration table forming. When slump exceeds 70 millimeters, manual rotting molding is advisable. Preparation steps. Step 1. The concrete mixture must be taken from 3 locations. Sampled from the above different locations. At least mix back and forth 3 times with a shovel. Step 2. Vibration table molding. One-time mold filling. Insert and compact with a trowel along the wall of the test mold. Concrete above the mold. The test mold shall be attached or fixed to the vibration table. Vibration should continue until the surface exudes slurry. Should not be over-vibrated. Then scrape off excess concrete. Level the surface with a trowel when the concrete begins to set. Step 3. Manual rotting molding. Fill the mold in 2 layers. Each layer approximately equal in thickness, along the spiral direction from the edge. Perform uniformly in the middle. 1 rotting bottom layer concrete. Rotting shall reach the bottom of the test mold. Vibration shall penetrate 20-30 mm into the lower layer. Maintain verticality during rotting. Finally, use a trowel along the inner wall of the test mold. Insert and pull out several times. Here, we need to pay attention to tamping times. No less than 12 times per 10,000 square millimeters. Gently tap the surroundings with a rubber hammer. Eliminate voids. Scrape off excess concrete. Level the surface with a trowel when the concrete begins to set. Step 4. Insertion type vibrator forming. One-time mold filling. Use a trowel to rod along the inner wall. Make the mixture above the test mold. It is advisable to use a diameter of 25 mm. Insert vibrating rod 10-20 mm from the mold bottom, and must not touch the test mold base plate. Vibrate until slurry emerges on the surface. To avoid excessive vibration causing concrete segregation. General vibration time 20 seconds. Slowly withdraw the vibrating rod. Scrape off excess concrete. Level the surface with a trowel when the concrete begins to set. Specimen curing. After forming, cover the surface with waterproof film. Standard curing condition method. In an environment with a temperature of 20 plus or minus 5 degrees Celsius. Stand still for 1 to 2 days. Then perform numbering. Demolding. Curing in a standard curing room. General temperature 20 plus or minus 2 degrees Celsius. Humidity above 95%. The standard curing time 28 days. Non-standard curing time 1, 3, 7, 60, 90,000, 180 days. Compression strength test. Test steps. Step 1. Inspect the press. Step 2. Sampling test. The specimen surface and bearing surface must be kept clean. The bearing surface of the specimen shall be perpendicular to its formed top surface. Align the specimen center with the center of the testing machine's lower platen. Adjust the spherical seat to ensure balanced contact. Step 3. Uniform loading. Concrete with a strength grade less than C30. Use a loading rate of 0.3 to 0.5 megapascal/s. When the strength grade is greater than 30 and less than C60, then adopt a loading velocity of 0.5-0.8 megapascal/s. Concrete with strength grade higher than C60. Apply a loading rate of 0.8 to 1 megapascal/s. Step 4. When the specimen approaches failure and begins to deform drastically, stop loading until failure. Record the failure load. Calculation and evaluation of results. First, determine the formula to be used as FCC equals F/A accurate to 0.1. Second, strength evaluation. Generally, the average value is taken. One of the maximum or minimum values. When the difference from the intermediate value exceeds 15%, take the intermediate value as the test value. If the maximum difference between the minimum value and the intermediate value, when both exceed 15%, this group of specimens is invalid. Example: the strength test value of a certain group of concrete specimens is 28.2 megapascals. 36.5 megapascals, 30.2 megapascals. Determine the strength value of the modified specimen group. Intermediate value 30.2 megapascals. Difference 30.2 minus 28.2 equals 22 divided by 30.2 equals 6.6% is less than 15%. 36.5 minus 30.2 equals 6.36. 3 divided by 30.2 equals 20.9% is greater than 15%. Test value. Take the median value of 30.2 megapascals. In this lesson, we are learning mechanical properties of concrete, concrete specimen preparation method, and test method for compressive strength of concrete. Hope you master the relevant knowledge points in future work. With a meticulous work attitude, contribute to the strength of the transportation country.